You are probably familiar with what happens to an open container of water that you just leave out on a counter. In time, the water will evaporate. Okay, so how does that happen? That happens because molecules from the liquid start going into the gas phase. And that is because there are collisions of water molecules with the surface of the water, and some of them have sufficient energy to escape the liquid phase and go into the gas phase, even though liquid phase is the dominant phase that it's in. Okay, so there's collisions at the surface. Okay, but what happens if you close that container? And what happens is you keep having molecules go into the gas phase, but at some point the number of collisions going out of the liquid phase and the number going back into the liquid phase will equalize each other because they're trapped. Okay, these over here can escape and they aren't real likely to come back and hit the surface, so it keeps evaporating. But at some point, if it's closed off, you will have a pressure, a number of molecules in the gas phase, and it reaches an equilibrium, and the number of collisions going out of the water will equal the number of collisions going back into the water. Okay, so we have collisions down equaling number of collisions up. And that will happen at equilibrium, and then the pressure at that temperature is the vapor pressure for that for water. And so if we have at a certain temperature, we'll have a certain number of vapor molecules, but then if we raise the temperature, we will have more molecules have enough energy to get out of solution, and you'll have a higher vapor pressure at a higher temperature. So let's look at that on a graph. We have a number of molecules versus the speed of the molecules, and we have a distribution at a certain temperature. So this is some temperature T1. And let's say that we pick some speed that a molecule needs in order to have sufficient kinetic energy to break the intermolecular forces and escape the liquid. Okay, so this area here represents all the molecules that have enough speed to break the intermolecular forces. And of course, it's really kinetic energy. Okay, so then if we raise the temperature, the distribution at a higher temperature than T1, the distribution shifts to higher speeds and spreads out, and therefore if we have the same temperature where the molecules can escape, you will have more of them, more of the molecules in the liquid have that energy to escape. So at higher temperatures, you will have more of them escaping. All right, now how does that relate to boiling? Because boiling is clearly going from a liquid phase to a gas phase. All right, so we have our open container, and generally there is some air above it, and the air molecules are also pushing down on the surface. And at the same time, the water molecules are pushing up. Okay, so air is pushing down, water is pushing up, and as you raise the temperature, you're not changing the pressure in the air if you just heat underneath, but a flame underneath. You're heating the water, but you're not heating the air, so the number of collisions of the air haven't changed, but the number of water collisions there have been more of them that have enough energy to escape. Okay, so more water leaves the vapor phase, and boiling will occur when you have so much vapor pressure that the vapor pressure of the water is greater than the air pressure. So that's what boiling is, when you have enough vapor pressure of the water, a sufficiently high temperature that vapor pressure is greater than the air pressure. All right, and we can compare boiling points of different substances by looking at their intermolecular forces and seeing how strong they are, because the more intermolecular forces they have, the more heat it takes to break them. All right, so first, try this. Look at these four and identify what intermolecular forces you need to overcome boiling. What intermolecular forces you need to break in order to boil that substance. So stop the video, and I'm going to tell you the answers now. Water is hydrogen bonding. Methane has no dipole, so that's dispersion. CCl4 also has no dipole, so it's dispersion. And sodium chloride, that's an ionic compound. So that's the intermolecular forces for it are just the ionic bonds. All right, so you can use those and rank them according to how high you expect their boiling points to be. Okay, the stronger the intermolecular force, the higher the boiling point. All right, so the highest boiling point is going to be the strongest force, which is going to be ionic. So sodium chloride will have our largest boiling point. The next highest would be hydrogen bonding, so that will be water. And then you have two that are dispersion. How are you going to compare those? Remember, we can compare dispersion based on size or based on shape. These two have the same shape, so it's on size. And you can say that there are more intermolecular forces for the larger size, so it's going to be harder to boil that, and methane is going to be the easiest to boil. All right, now let's look at some liquid properties that also depend on intermolecular forces. The first one is surface tension. Okay, surface tension, if you look at, on kind of a molecular view, look at a glass of water, or any other liquid for that matter, we're drawing the molecules as circles, and you have forces, intermolecular forces, on any particular one molecule going all kinds of directions except up. Okay, if you look at one that's inside, it's got intermolecular forces pulling it every which way because there's molecules all around it. But the surface ones are only being pulled sideways and downward, which creates what we call surface tension, kind of almost a layer of surface tension. So the forces pull the surface molecules downward. And we can talk about surface tension as an energy per surface area. So units can be something like joules per meter squared. And we also note that the stronger the intermolecular forces, the greater the surface tension. So we can then rank things. Okay, for instance, we can compare, I can tell you that mercury has metallic bonds. Okay, so the intermolecular forces there are metallic bonds. That will have a very large surface tension, and water will have weaker but still pretty strong. Okay, so it has hydrogen bonding. And weaker than that would be something with hydrogen bonding but not quite as much per unit area. Okay, so this is less H bonding. And then something with just dipole-dipole. We'll look at diethyl ether. We'll have even less. So that's dipole-dipole. Okay, so we expect surface tension to be greater the greater the intermolecular forces. All right, so you can try some. How would the following liquids compare in terms of surface tension? So compare the forces, first label the forces, and then rank them according to that. So CH3F is going to be dipole-dipole. CH3CH3, or ethane, is going to be pure dispersion. And methanol, CH3OH, is going to be hydrogen bonding. So the strongest is going to be hydrogen bonding. And less than that will be the dipole-dipole. And less than that will be the dispersion forces. Okay, and we can look at a picture of an insect known as a common water strider, which takes advantage of the fact that water has a high surface tension. So they scoot about on the surface of the water, and if water didn't have such strong intermolecular forces, they would not be able to hold up on that water. They would sink. Okay, so that's crucial to their lives. All right, and the final liquid property I want to look at in terms of intermolecular forces is viscosity. Viscosity is a resistance to flow. So something is more viscous if it's thicker, like honey is viscous and water is not so viscous. And so we can again look at intermolecular forces. The greater the intermolecular forces, the greater the viscosity. So we can look at one particular type of intermolecular force and compare them for expected viscosity. So let's look at these three molecules. We have methanol, CH3OH, which is going to have hydrogen bonding. We have ethylene glycol, used in antifreeze. It also has hydrogen bonding, and it also has one OH group for every carbon, just like methanol. And then we have glycerin, which has, again, one OH group for each carbon. So they have, in some ways, very comparable hydrogen bonding. So since they all have the same type of bonding, we can compare based on size or shape, and in this case it's mainly going to be size. Okay, so the size of the molecule gets noticeably larger as you go to the left, so the viscosity is also going to increase going to the left. And if you've ever seen glycerin, it's a very thick substance. It's much thicker than these other two. And ethylene glycol by itself is more syrupy, thicker than methanol. All right, so let's finally look at varying temperature and see how that affects viscosity. And you may have used the fact that increasing temperature lowers the viscosity in your everyday lives. Okay, so higher temp makes lower viscosity. Okay, so if you've ever had honey stuck in a jar and you want to get it out, you might microwave it, you might heat it to lower its viscosity. Another example is when you want to change the oil in your car, you generally drive it around and warm it up so that the oil becomes less viscous and will flow out more readily. But how can we explain that in terms of molecules and speed? We can do that by looking at a speed distribution for a certain temperature again, T1, and then look at the distribution for some higher temperature. Remember, it gets broader and the average becomes higher. So we'll say that's higher T for this one. And again, you can look at some position of some speed of molecules that you want, and for the first temperature, you're going to have this many molecules that can exceed that speed and flow. But as you raise the temperature, you greatly increase the number of molecules that can do that. So you can also add these molecules as you increase the temperature. So you get more and more molecules that can flow more readily as you increase the temperature.